Alright, today we get to talk about entropy. And as everybody knows, entropy is a measure of disorder. Your mom looks in your room and says, "Wow, the entropy of your room is much higher than it was yesterday." And we like to joke about entropy and disorder, but what does it really mean? If you went to put a number on how messy your room was, what number would it be? Alright, so we're going to talk about that. And it turns out, I think the best way to understand entropy is in terms of micro and macro states. So let's say, for example, I'm flipping coins. Let's imagine I have 3 coins. I'm going to throw them on the ground and see which ones come up heads and which ones come up tails. Let's imagine, if you will, that I throw the 3 of them on the ground, and one time I get the first one comes up heads, the next one comes up heads, and the last one comes up heads, right? But another possibility is maybe the first 2 come up heads and the last one comes up tails. Or maybe the first one and the last one come up heads, but the second one comes up tails. Or maybe the first one comes up tails and the other 2 come up heads. Or maybe I have the first one come up heads, but the other 2 come up tails. Or maybe the first one comes up tails and the last one comes up tails, but the middle one comes up heads. Or maybe the first 2 come up tails and the last one comes up heads, right? Or possibly they all come up tails. And I think I've covered all the possibilities I can get with 3 coins. The more coins I get, the more possibilities. The possibilities just explode, right? That's why I stuck with 3 coins. Okay, this is what we would call the microstate of the system. Everything there is to know about my system is described. I tell you for each individual coin whether it is heads or whether it is tails. But maybe you don't care what each individual coin is doing. Maybe what you care about is just the total number that came up heads. Right? Maybe you're playing a game with your friends and he says, okay, you throw these three coins on the ground, everyone that comes up heads you get to keep, and everyone that comes up tails I get to keep. You don't care which ones comes up heads, you just care how many come up heads, right? So in this case we had 3 of them come up heads. This one we had 2 heads, 2 heads. Alright, here we have 2 heads, 2 heads, 2 heads, 1 head, 1 head, 1 head, and none. Okay? So this is the microstate of the system. If I look right here, if this happened, the microstate would be, right, coin 1 is tails, coin 2 is tails, and coin 3 is heads. The macrostate is just, there's 1 heads. Alright? So the macrostate, for a given macrostate, there may be more than 1 microstate that describes that macrostate. Okay? It turns out the entropy has to do with how many microstates there are for a given macrostate. Alright? If there's only 1 microstate, there's no entropy. So for the macrostate of 3, if I say what is the entropy of having all 3 come up heads, the entropy is 0. There's only 1 way to realize it. Okay? But the entropy is higher for the macrostate where I have 2 heads, because there's 3 different ways to realize it. So entropy has to do with the number of microstates you can use to realize a particular macrostate. So entropy is an average, it's a statistical quantity that we apply to something that tells us how many different ways could you arrange this system and still get the same macrostate. When we talk about thermodynamics, the microstate for an ideal gas would be knowing where every particle is and how it is moving, right? But we usually don't care about every single individual molecule in our 10 to the 22nd molecules or whatever in our gas. What we care about is the pressure and the temperature, things like that. So pressure and temperature are things that describe the macrostate. So if I have a gas with a certain volume, pressure, and temperature, that describes its macrostate. How many different ways could I arrange the molecules in that gas to get the same macrostate? How many different microstates could I use in order to realize that same macrostate? And that's what entropy has to do. And as you can imagine, for gas in a box, in a reasonable size macroscopic box with a macroscopic kind of quantity of air in it, there's going to be lots and lots of different microstates you can use to realize a given pressure, volume, and temperature. Alright? So macrostate, macro is like pressure, volume, and temperature. whereas micro is what is each individual molecule doing. Okay. Now, entropy, as I said, is about probability. It is very improbable that we will ever observe a process that decreases the entropy of in a real physical process. In the limit as n goes to infinity, that's horrible grammar, sorry about that. In the limit as n goes to infinity, probability becomes fact. Okay, so what do we mean? Consider the air in the room that you're in, all right? If there were only one molecule of air in the room, chances are pretty good, if you looked at some particular time, that you would find that that one molecule was in the west half of your room, right? About half of the time you'd find it would be in the west half of the room. If you had two particles, it would be less probable that you would find both of them in the west side of the room, but not completely improbable, all right? About a quarter of the time you would find both of them in the west side of the room. But as you add more and more molecules, the probability of finding them all in the west side of the room vanishes, right? When you have 10 to the 22nd, 10 to the 23rd particles zipping around in your room, the chances that all of them are on the west side of the room at any given moment in time, it's just so small, you might as well just call it zero. And in the limit, as you have an infinite number of particles, it really does become zero. So entropy is a probabilistic rule. It does not, when we talk about the second law of thermodynamics and entropy increasing, that does not apply to a system with very few degrees of freedom. All right? But for most macroscopic stuff, there's so many different degrees of freedom, there's so many variables to keep track of, that you might as well take entropy as an absolute law. All right? Because you're in the statistical limit. Okay. Entropy is different things for different people. We're going to talk about entropy in its thermodynamic definition in this class, but there are other ways that people use entropy, and you use the same ideas. You develop intuition for entropy using thermodynamics. It will be useful for other things that you may do in your life and your career. In thermodynamics, we define entropy this way. I like to take the quantum mechanical rather than the classical version of thermodynamics, just because it's actually easier when we quantize things. So what I like to say is, okay, I've got this gas in this box. It's got a certain pressure, temperature, and volume. How many different quantum mechanical states can realize that same pressure, temperature, and volume? All right? And we're not going to actually, you don't know quantum mechanics yet, so I'm not going to make you calculate that, but that's the basic idea you should have in your mind. We'll give you another more practical equation later that you can use for your homework problems. But I just want you to know where that equation comes from. And it comes from this definition right here. If I count the number of ways I can arrange particles to realize a certain macrostate, if I take that number of ways, take the natural log of it, and multiply by Boltzmann's constant, that is what we mean by entropy. So if there's more microstates that realize a particular macrostate, the logarithm of that will be bigger and the entropy will be bigger. All right? Now it turns out you can use entropy in other fields. For example, if you are an electrical engineer or a computer scientist, or if you're in information systems, you'll probably learn about something called Shannon's information theory. And in Shannon's information theory, they will define the Shannon entropy. And the Shannon entropy is the entropy of information. So imagine you have a file, and it's made up of bits, right? Ones and zeros, right? And so forth. Imagine you want to compress that file. You want to do it in a non-lossy way, not like JPEG compression where you throw information out, but like a zip file where you have some file and you want to compress it and make it smaller so it takes up less space on your drive, so that it takes less bandwidth to transmit, and so forth. How much can I compress a piece of data? Well, if my data is 1,000 ones or 1,000 zeros, I don't have to send 1,000 bits to say it's 1,000 ones. I can just say, look, it's a 1 and there's 1,000 of them, right? So you can compress that very well. That's because that is a macrostate, your macrostate, 1,000 ones. There's only one microstate that describes that. So that is a zero entropy state. You take the logarithm of how many ways you can realize 1,000 ones, and it's zero. All right? There's one way, take the logarithm, you get zero. So that means you can do a lot of compression. But if I had some string of 1s and 0s such that half of the bits were 1 and half of them are 0, that's a maximum entropy state. All right? There are lots and lots of ways that you can write 1,000 bits where half of them are 1s and half of them are 0s, right? So that is a maximum entropy state, which is going to be harder to compress. All right? So Shannon's information theory uses entropy. When you parallel park a car, you may have noticed that parallel parking is not trivial. It can be a real pain. You have to practice it before you get your license. All right? But pulling out of a parking spot is not that difficult. Why is that? That's because there's a very small number of ways you can be in the parking space, but there's a large number of ways you can be out of the parking space. So when you're parking, you're going from a high entropy to a low entropy state, and that's hard. When you're pulling out of a parking space, you're going from a low entropy to a high entropy state, and that's easy. The clutter in your room, right? Your mom comes and says, why are all of the books off of your bookshelf? That's a high entropy state. Why is that a high entropy state? Because there is a small number of ways that you can arrange the books on your bookshelf compared to the number of ways you can arrange them flopped all over your room. All right, so the macro state is the books are all on the bookshelf or the books are strewn throughout the room. Strewn throughout the room can be realized by more microstates, so that macro state has a higher entropy. Okay, now that's entropy. Next we need to understand what a reversible or an irreversible process is. Irreversible processes are things like an adiabatic free expansion, right? Not an adiabatic, nice reversible adiabatic process, but this is the one where we have gas in a box and I open the lid of the box and the gas spreads out throughout the room, right? That's not reversible. If I close the lid, the gas will not go back into the box, right? If you played a film of me opening a box of gas and the gas came out and filled the room, if you played that backwards and saw the gas go back into the box, you would say, that is really fishy. That just ain't right. All right? Heat conduction from something hot to something cold. If I have a hot piece of metal at T hot and a cold piece of metal at T cold and I put them together and heat conducts from one to the other until they reach equilibrium, you wouldn't expect that to happen backwards. You wouldn't expect two pieces of metal at the same temperature to spontaneously have heat flow to make one at a higher temperature, one at a lower temperature. That is irreversible. Scrambling eggs is irreversible. If I scramble eggs with a fork and then I stop and I move the fork backwards, you don't expect to get the yolks to come back together, do you? If you watched a video of me scrambling an egg backwards, it would just look wrong. All right, so that's what irreversible processes are. Reversible processes are something like an adiabatic expansion. If I have a piston of gas, all right, or an ideal basketball, how about that? I drop an ideal basketball on the floor, it compresses adiabatically, then it expands adiabatically and comes back up. Now with my ideal basketball, you watch the film forwards and backwards, you see a ball bouncing. No big deal, all right? Now a real basketball is different. It turns out reversible processes are theoretical things. In real life, everything's really sort of irreversible, right? In my basketball, it's not a perfect adiabatic compression. It's not a perfectly adiabatic expansion. So that a real basketball would be an irreversible process, whereas my ideal basketball is reversible. If I played a film of me dropping a basketball, right? If you videotape that, the ball will fall down, it will bounce, but it won't come up quite as high as where I dropped it from, because it's not truly a reversible process. If you watch that film backwards, you'd see a ball falling some distance, bouncing, and then coming up higher than it started from. And you would say, that's screwy, that's wrong. All right? Now, it could happen, right? I mean, physics works the same backwards and forwards, except for probability. There's lots and lots of particles of gas involved in that expansion and that compression. So, what we expect is when I drop the ball, because it's irreversible, entropy increases and it can't go backwards. All right? So my ideal basketball doing an ideal adiabatic compression expansion, that's reversible. A real basketball is irreversible. A constant temperature expansion. That's an example of an ideal process. Imagine I have some piston in ice water. All right? So as the piston expands, heat flows in from the ice water to keep the temperature constant. All right? Now, if I push the piston back down and do a compression, it looks pretty much the same. And if you filmed me doing one or the other and then played it backwards, you wouldn't know I was doing it backwards. That's reversible. These two reversible processes, incidentally, are the reversible processes that Carnot chose to use in his Carnot cycle, right? We needed reversible processes. That's what he used. Ice melting is sort of an example of a reversible process. Now imagine that someone did some nice ice sculpture of a duck and it melted, and then you froze it again. It wouldn't go back to a duck. So in that sense, it's not reversible. But in the thermodynamic sense, where we don't care what shape it's in, we just care the volume it occupies and what phase it's in and so forth, it is reversible. If I take water and put it into a freezer, and the freezer is infinitesimally below 0 degrees C, heat flows out of my water at 0 degrees C and ice forms. Now if I make the freezer infinitesimally above 0 degrees C, now heat flows in and melts the ice. You film it, play it forwards, backwards, it all looks the same, okay? Heat conduction can be reversible, right? Now this thing right here, we said this is not reversible, right? When I'm conducting heat from something hot to something cold. But what if I'm conducting heat from something hot to something at the same temperature? Also hot, right? I can put a little tiny bit of heat from one side to the other. And as long as it's an infinitesimal amount, so the temperatures don't change appreciably, if I did that backwards, if the heat flows back, that's fine, right? So infinitesimal heat flow between two things at constant temperature is reversible. All right? So basically, reversible things are things that won't happen backwards in nature. It turns out in nature, pretty much everything is irreversible. But irreversible things are things which don't happen backwards in nature. So almost everything that happens in nature is irreversible, which means that they don't happen backwards in nature. If I played a film backwards, the physics would cry, right? If I played a film of me scrambling eggs and then played it backwards, physics says, no, you don't get the yolk back, all right? Newton's second law says you can get the yolk back, right? Physics is reversible, but statistically, there's so many particles involved in the egg that once you scramble them, they're not going to just come right back together again. All right, so entropy, when we talk about reversible versus irreversible, it's a statistical thing that's true because we have a large number of degrees of freedom, large number of particles. Reversible is something where we can play the film backwards and physics doesn't mind, all right? I'm walking down the street, throw my keys in the air, catch them. You play that backwards, you see another parabolic trajectory, and physics is happy, all right? So that's sort of reversible. Until you start looking into the fact that, I'm sweating, I'm metabolizing, I'm doing all of these things that are irreversible, and then you say, okay, really anything in real life is irreversible. But that's almost reversible. If I'm just looking at the key's trajectory in space, totally reversible, okay? Next thing we need to understand is the difference between an isolated and an open system. An isolated system is one in which heat cannot flow in or out. Okay? So, for example, imagine I have two pieces of metal, a hot one and a cold one. I put them together, all right? But I don't let any heat flow outside of this system. This is my whole system. No heat flows in or out of it, all right? Heat's going to flow from the hot thing to the cold thing. In the process, the entropy will increase, all right? So in an isolated system, the entropy can never decrease. Here's an example of the entropy increasing, all right? So in an isolated system, entropy cannot decrease. But an open system is one in which heat can flow in or out. So for example, if I put my two pieces of metal together, but I'm only considering what happens to the hot piece. So my system is just the hot piece of metal. All right? This is not an isolated system, it's an open system because heat can flow out of it. All right? So this is an isolated or closed system because I'm considering the whole thing and no heat can flow in or out. But if I look just at the hot piece of metal, that is an open system because heat can flow in and out of it. All right? It's in thermal contact with something. If I look at this, heat's flowing out, this cools down. It turns out the entropy of this part will decrease. That's okay because the entropy somewhere else is increasing. All right? So, for isolated systems, the entropy cannot decrease. And it turns out for an isolated system, for an irreversible process, the change in entropy has to be greater than 0. For a reversible process, the change in entropy has to exactly equal 0. Why is that true? Well, imagine an adiabatic compression. Imagine I have some piston and I compress some gas adiabatically. Well, we say this is an isolated system, right? No heat's flowing in or out of it. And I said for an isolated system, the entropy cannot decrease. It can only increase or stay the same. Well, let's imagine we took the option and said, well, maybe it's increasing, right? It's an isolated system. It's allowed for the entropy to increase. Well, what happens if I do it in reverse now? It's a reversible process. If the entropy increased when we went one way, it must decrease when we go the other way. But the entropy cannot decrease in an isolated system. So we say, therefore, if it's a reversible process, the change in entropy must be 0. For an irreversible process in an isolated system, the entropy increases. For a reversible process, it stays the same. What about an open system? For an open system, it's an open question. The change in entropy can be anything. Here we saw an example of the entropy going down. Heat flows out of this piece into this piece. If we consider this piece right here to be our system, the entropy of that system goes down. If I look at this piece right here, the entropy of that system goes up. So it can go up, down, stay the same, whatever, if it's an open system, because the entropy is going to be changing somewhere else outside of our system that can compensate if it so happens that the entropy in our system goes down. All right, now how do we calculate the change in entropy for a system? Well, here's the equation we use. The change in entropy is just the integral of dq over t from our initial to our final state. But note, our dq has this little tag on here that says reversible. What that means is that this equation is only valid for reversible processes. All right, so let's consider some reversible processes. Ice melting. I have some ice in the freezer at my freezer's 0 degrees C, infinitesimally above 0 degrees C, so heat flows out and the ice melts. All right? Or maybe, what if I take it out of the freezer? All right? Okay, it's still a reversible process for the ice, even though it's not reversible for the whole system. Right? We would never expect to see heat flow out of cold ice or cold water into a warmer room to freeze ice, right? But as far as the ice is concerned, we don't care whether the heat's flowing into a freezer at 0 degrees C or into a room at 20 degrees C, right? We're just looking at the ice. So the ice melting, as far as the ice is concerned, is reversible. So we can use our equation. The change in entropy is just going to be the integral from our initial to our final state of dq reversible over t. All right, but what is dq? Well, q for melting, right, it's just the mass that we melt times the latent heat. Well, if I only melt a little bit of mass, then it only takes a little bit of heat. So there's the equation, all right? So I'm just going to plug that in. This is the integral from my initial to my final state. And I plug this in for dq. Let's put the L out front so it's clear that that's not part of my infinitesimal thing. All right? And then the L comes out of the integral. The temperature of my ice doesn't change while it's melting, right? It starts melting at 0 degrees C and it finishes melting at 0 degrees C. Only we don't plug in 0 degrees C, do we? Because this is an absolute temperature, it must be in, dun dun dun, Kelvin. All right, so we pull these out because they're constants, so we just get L over T, integral of dm from my initial to my final state. This is how much ice is melted. Initially I have no ice melted. By the time I get to the end, I've melted all of the ice, and I find that the change in entropy is just L over T times the total mass of the ice that I melted, where the temperature here is in Kelvin. Okay, so it's not too hard to calculate how the entropy changes when ice melts, all right? When ice freezes, all right, the heat flows the other way, and we just get a minus sign right here. It's reversible, all right? Okay, what about an isothermal expansion? Imagine that some gas expands isothermally, all right? As far as the gas is concerned, that's a reversible process, all right? It's possible that I could do this reversibly, putting my gas in ice water or whatnot. But the gas doesn't care whether it's in ice water. It doesn't care if the entropy of the universe is changing or whether the whole thing is reversible. What's happening just to the gas is reversible. All right? So that means we can calculate the change in entropy for our gas. Wait a minute. The change in entropy should be 0 for a reversible process, right? No. The change in entropy is 0 for a reversible process in an isolated system. An isothermal expansion does not happen with an isolated system. As my gas expands, it tries to cool down. If I want to keep it at constant temperature, heat needs to flow in from somewhere. So this is not an isolated system, all right? So because it's not an isolated system, even though it's reversible for the gas, all right, it may not be reversible for the universe, or even if it is reversible, there's another entity involved here. And My gas, its entropy can change because the entropy of something else is also changing. All right? So let's just calculate. For my isothermal expansion, we do this integral, dq over t, from the initial state to the final state. All right, once again, we know this is reversible, so I just calculate, right? I just say, oh, it's just dq over r, without even knowing what q is. I know, however, as I put heat into my system, temperature is not going to change, so the temperature comes right out of this equation, and I just have this, and I go, oh, well, I integrate dqr from my initial to my final state, and I end up with just all the heat that I put in. So if you calculate how much heat comes in an isothermal expansion, divide by the temperature in Kelvin, you will find how the entropy changes for an isothermal expansion. Now, as the gas expands, heat flows in, so Q is positive. So an isothermal expansion, when I go from, this to this, the entropy of my gas increases. And you can kind of think of that this way. There's two different parts of entropy for an ideal gas. There's how the particles are distributed and how they're moving. If the temperature doesn't change, kind of the energy, the kinetic energy, the internal energy, that doesn't change. So you don't have more ways to rearrange the energy. But by going to a higher volume, you have more ways you can rearrange where the particles are located. So yeah, if I expand, it seems like the entropy ought to go up. An isothermal compression, I compress it, heat flows out, this will be negative, and I find the entropy goes down. Pretty cool. And it's reversible, so the entropy when it goes up is the opposite of the entropy change when it goes back to its original state. Now it's reversible for the gas, maybe it's not reversible for the universe, maybe there's some other thing, right, and its entropy changes in ways we didn't calculate. Okay, so we know how to calculate entropy change for reversible processes. We have this wonderful integral, right? The change in entropy is equal to the integral from our initial to our final state, dq reversible over t. What if we do a non-reversible ideal gas process? Like, for example, how do I calculate the entropy change in a free expansion? Okay, well, here's the thing you need to remember. Entropy, the entropy of a system only depends on its state, not how it got there. Right? We talked about how if I look at a PV diagram, if I know where we are on a PV diagram, I know the temperature of the gas. Doesn't matter how I got there, the temperature is the temperature. Whereas the work that's done when I go from point A to B depends on what path I take to get there, the change in temperature doesn't. Entropy is a state variable, like temperature. It doesn't matter how we got there, the change in entropy is the same. So if I have a non-reversible process, I just have to think of a set of reversible processes that will get me there. And it turns out, if you sit down, you can actually do a derivation and show that there's a general formula you can always use for any process. Pick any path will do, pick one you can calculate, and it turns out you can sit down and say, if I have two arbitrary points in my PV diagram, I can connect them with a bunch of processes such that the change in entropy is this. And as I pointed out, it turns out there's two things that affect the number of microstates we can get, and therefore the entropy. That's how the particles are moving, right? And how the particles are moving has to do with temperature, right? And how we distribute them in space, that has to do with the volume. So you get one that has to do with temperature and one that has to do with volume. All right? Okay, so this equation is really nice. The book does a derivation of it. I'm not going to do it. Really slick. All right? If you want to understand differential calculus, it's a great exercise. I recommend you work through it. It's really cool. But the coolest thing about it is that you get this result and you've got an equation. I give you any problem on the homework, any problem on the exam, and I say, here is this gas. It does this process. If you can find the initial and final temperatures and volumes, you can find the change in entropy with this equation. There you go. So let's consider a free expansion. All right? For a free expansion, I say, okay, it's not a reversible process. But if I can think of a reversible process that gets me from the final state to the end state, I can use those reversible processes to calculate the change in entropy. All right, so I start with my gas all on this side of the box, and then I've got my gas all on this side of the box. All right, how could I do that? Maybe I do an isothermal expansion, right? That gets me from this state to this state, right? Because in a free expansion, the temperature doesn't change, just the volume. So I go, oh, an isothermal expansion will give me the answer. And then I say, oh, what's the entropy change in an isothermal expansion? Well, I know what it is because the entropy change is always this, and really, I didn't even need to think about what reversible process gets me from point A to point B, because I know there always will be one, and this equation will describe it. So I didn't even just need to stop and think about how I could get from point A to B. I just pull this out and I say, oh, the temperature doesn't change, so it's going to be the natural log of 1, that's 0, and it's just going to be nr natural log V final over V initial. So, haha, change in entropy is nr natural log of V final over V initial. Why? Because this equation covers everything, and the temperature doesn't change in a free expansion, so that term goes to 0, and I'm just left with that one. Simple, huh? How about a free, okay, yeah. How about a free expansion followed by an isothermal compression? What's the change in entropy for this? So I start with all my gas on one side, then I do a free expansion. I let the gas come out and expand, all right? And then I'm going to compress it back where I started from isothermally. So I'm going to compress it isothermally, so we're back to this state. Well, a free expansion doesn't change the temperature. A compression, isothermal compression doesn't change the temperature. So as I go from here to here, the change in temperature is 0. The change in volume is also 0, right? We got bigger, but then we got smaller again. So if I look at my equation, I go, oh, if the temperature doesn't change and the volume doesn't change, the entropy doesn't change. And that makes perfect sense, because entropy doesn't care how we got there. It's just a variable of state. We are in a state here. We're in the same state at the end, so the entropy didn't change. Now, is this a closed system? For the free expansion, the system was closed, right? For the free expansion, the entropy went up, all right? Right? The entropy goes up if the final volume is bigger than the initial volume, all right? And it goes up because it's an irreversible process. But wait a minute, if the volume went down, then I'd get negative change in entropy. But that's okay, it can't go down. You can't just suddenly put the wall in and have all the gas go back there, because it's an irreversible process. That's the whole point. So for this first step, the entropy goes up. For the next step, the entropy goes down. Is that allowed? Well, yes, because this last step has to involve thermal contact with something else. This, for this last step of compressing it, this is not an isolated system. It's okay for the entropy to go down if it's not an isolated system. All right? So the net change in entropy from here to here is 0, because we start and end at the same state. All right, how about the entropy of conduction? Imagine I have something at T cold and something at T hot, and heat flows from one to the other until the whole thing comes into equilibrium at T final. How much does the entropy change? This is not a reversible process. So we need to think of a reversible process that gets us from point A to point B, all right, from the beginning to the end. Well, let's imagine here's my reversible process. I'm going to separate the two, put T hot over here, put T cold over here, and I'm going to take T hot and put it in contact with a giant thermal reservoir at T hot. Now, I'm not really doing this, right? Because I only need to do this mathematically. I only need a thought way that I could do this in order to so I can use my integral to do my calculation. All right? So let's imagine I put it in a thermal reservoir at the same temperature, and I let just a little bit of heat flow out so that the temperature changes just a tiny, tiny bit. All right? So now the temperature is T hot minus delta, and I had this little bit of heat flow out. This is reversible, right? Heat flowing between two things at the same temperature is reversible. But I can only let an infinitesimal amount flow, or the temperature will change. So what I'm going to do now is I'm going to take this bar right here, I'm going to take this block, which is now at temperature T hot minus delta, and I'm going to put it in thermal contact with a different thermal reservoir at temperature hot minus delta. And I'm going to keep doing this, all right? And each time I do this, I'm going to get a little bit of heat that flows out. And how much heat will flow out in each step? Well, it's going to be mc, the heat capacity, the mass times the specific heat, times this infinitesimal little bit of temperature that comes out, right? So if I had a finite amount of temperature change due to a finite amount of heat, that would be irreversible. But if I do infinitesimal stuff, then I'm okay. And then I can say, oh, here's a dq I can plug into my integral, right? So the change in entropy for the hot piece is just going to be the integral from the initial state to the final state of dq, which is mc dt over t. mc your constant, that comes out, then I get the integral of dt over t, so that's going to be natural log of t, and I evaluate that between my initial and my final temperature, and so it's going to be T final divided by its initial temperature is T hot. All right? Final temperature is lower than the initial temperature. That means this is going to be the natural log of something less than 1, and the change in entropy is going to be negative. Is that okay? Yes, it's okay because it's not a closed system. The entropy of my hot piece can go down because the temperature of the cold piece will go up. What's the change in entropy for the cold piece? Well, it's going to be the same logic, only now it's going to be, maybe I should say mass hot, C hot, right? Because maybe they're different masses and different materials. So, but here we have the cold thing, specific heat of the material the cold thing's made of, and then you get natural log of T final over T cold, right? So the total change in entropy is just going to be the sum of those two. Mass hot, C hot, natural log of T final over T hot, plus mass cold, specific heat of the cold thing, natural log of T final over T cold. All right? Now, you can use that then to calculate how much the entropy changes when heat flows from one thing to another. Will this be positive, negative, or 0? Well, when I consider both of these objects together, I've got a closed system. I'm only allowing heat to flow from one of them to the other, not outside of the system. So it's a closed system. Is it a reversible or an irreversible process? Well, it turns out it is irreversible, right? I wouldn't spontaneously expect two objects in thermal equilibrium to suddenly have one of them get hot and one of them get cold. All right? So it's an irreversible process on a closed system, on an isolated system, so I expect the entropy to go up. So this should be positive. Now, you can, as an exercise for the reader, you know how to calculate the final temperature from the two initial temperatures and the heat capacities, right? Exercise to the reader. Show that this will always be positive. All right? You don't have to do that. It's really cool if you do, though. Okay. So now, the second law of thermodynamics. We said before that the second law of thermodynamics said that no heat engine can be more efficient than the Carnot efficiency. And then we said kind of an alternative way of stating it is saying that you can't get to absolute 0. If you could get to absolute 0, then the Carnot efficiency would be 100%, right? So kind of these two went together. If you assume you can't get to absolute 0, then you can't have perfectly efficient engines. If you assume you can't have perfectly efficient engines, that tells you can't get to absolute 0. All right? But there's a third way to state the second law of thermodynamics, and it's a more fundamental way. And that is basically this. The entropy of a closed system can't decrease. We've been talking about this, but now I'm telling you this is really the second law of thermodynamics. And it turns out from this one, you can prove this one, and you can prove this one. All right? So I consider this one the most fundamental way to describe the second law of thermodynamics. The entropy of a closed system can't decrease. All right? Remember, of a closed system, an open system, it can decrease. If I have some closed system and I look at just part of it, that piece of it is an open system, and that piece's entropy can go down. But the entropy of a closed system can't decrease. In fact, we could further clarify, once again, if I have a closed system and I do an irreversible process, the entropy will increase. If I do a reversible process, the entropy will stay the same. Okay. Now, because the universe is a closed system, its entropy must always be increasing. And that's what people mean when they talk about the heat death of the universe. Eventually, the entropy will reach a maximum state, and the universe will be chaos. You won't be able to extract energy from, right? In order to extract energy from heat, you know, mechanical energy, useful energy from heat, you need to have something hotter and something colder. Once the universe is at thermal equilibrium, we've reached maximum entropy, and everything kind of ends. Poof. Everything interesting in the universe will stop, all right? Now, what will happen, that's a long ways away. A lot of interesting things could happen. But that's what people talk about when they mean universal heat death of the universe, all right? The heat death of the universe is not something to worry about, though. It's a long ways away. All right. Now, can the entropy of something ever decrease? If it's an isolated system, a closed system, then no. But if it's an open system, it can. The entropy of thing A can decrease because maybe the entropy of thing B is increasing, all right? But the entropy of a closed system cannot decrease.